Tonight, we're going to follow the one rule of physics that every person on Earth has heard and push it right to the breaking point. The speed of light. The ceiling nothing in this universe has ever crossed. Physicists haven't just accepted that limit and moved on. They've been pulling it apart for over 100 years, studying what happens at it, what the math says about approaching it, and what the equations describe if you were somehow on the other side. What lies beyond the speed of light, according to the mathematics of physics, is a mirror territory where time runs backward, where mass becomes imaginary, where cause and effect trade places, and where the deepest law the universe enforces is not a speed limit at all, but something far more fundamental. By the end of tonight, you're going to understand why that barrier exists, what it is actually protecting, and why the most serious question in physics right now isn't whether we can break it, but whether the same equations that forbid it are also quietly describing a way through. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you already know. Light is fast. You've heard the number. 186,282 miles per second. That's the speed at which a photon travels through a vacuum. And it's the same for every photon that has ever existed, regardless of where it came from, how fast the thing that emitted it was moving, or which direction it was heading. The speed doesn't change. It doesn't add to the speed of the source. If you're aboard a spacecraft moving at half the speed of light and you switch on a flashlight, the light from that flashlight doesn't travel at 1.5 times light speed relative to the ground. It travels at exactly 186,282 miles per second, same as it always does, for everyone, without exception. This is not intuitive. It runs directly against everything your brain has been trained by everyday experience to expect. If you throw a ball from a moving car, the ball's speed relative to the road is your throwing speed plus the car's speed. That's how velocities add. That's how the universe appears to work from inside everyday life. Except it doesn't. Not for light. And not exactly for anything, once you start moving fast enough. This fact, the absolute constancy of the speed of light, is one of the most thoroughly verified experimental results in the history of science. Precision interferometers have confirmed it. Particle accelerators have confirmed it. The GPS network, which fails to function if you ignore it, confirms it millions of times per day. It is not in question. It is, if anything, more confirmed than most of the facts you take for granted about the physical world. Albert Einstein published his special theory of relativity in 1905. He was 26 years old and working as a patent clerk in Bern, Switzerland. The paper was titled On the Electrodynamics of Moving Bodies, and it started not from a laboratory experiment, but from a thought experiment he had been turning over since he was 16 years old. What would you see if you chased a beam of light and caught up to it? If you rode alongside it, matching its speed, what would the light look like? The wave would appear frozen, standing still, oscillating in space, but not propagating. But Maxwell's equations, the mathematical framework that describes electricity, magnetism, and light, don't permit a stationary electromagnetic wave. Light can only exist as a propagating disturbance, a wave that moves. A frozen light wave is not a solution to Maxwell's equations, which means the question has no answer within existing physics, which means something in the existing physics was wrong. The only resolution that preserved the laws of physics for all observers, regardless of how fast they were moving, was to accept something radical. The speed of light is the same for every observer. Absolutely. Unconditionally. And everything else, time, distance, mass, simultaneity, had to flex and bend around that fixed constant. Space and time were not absolute. They were relative. The speed of light was not. Einstein published this result in June of 1905, the same year he published papers on the photoelectric effect, for which he would eventually win the Nobel Prize, and on Brownian motion. It was one of the most productive years any single physicist has ever had. But of everything he published that year, the special relativity paper was the one that changed the architecture of physics. The implications follow directly, and they are strange in ways that took physicists decades to fully absorb. If two observers moving relative to each other both measure the same speed of light from the same light beam, and the speed is the same for both of them, then the space and time they each use to make the measurement cannot be the same. Space and time must be different for different observers. Different, not in the sense that they see different things because they're in different positions. Different in the sense that the distances are different and the time intervals are different. What gives is simultaneity. Two events that happen at the same time, according to one observer, don't necessarily happen at the same time, according to another observer, moving relative to the first. This is not a matter of signal delay. It's not that light takes different amounts of time to reach different observers and creates an illusion of different timing. The events genuinely happen in a different order, or simultaneously, or in the reverse order, depending on the reference frame of the observer. And there is no reference frame that is more correct than any other. All inertial reference frames are equally valid. The concept of absolute simultaneity, the idea that at the same time is a universal fact, doesn't exist. This was Einstein's most disturbing result. Not that things got heavier when they moved fast, or that clocks slowed, but that the present moment is not universal. That what is happening right now, somewhere else in the universe, is not a well-defined concept. That two people moving relative to each other can, with complete physical justification, disagree about the order in which two events occurred. What also gives is the rate at which clocks tick. A clock in motion, from the perspective of a stationary observer, runs more slowly than a clock at rest. The formula is precise. Your clock runs at a rate reduced by the factor gamma, which equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. Gamma is always greater than or equal to 1. At zero velocity, it equals 1. Clocks run normally. At any velocity above zero, gamma is greater than 1. Clocks run slow. At everyday speeds, the deviation from 1 is negligible beyond any possibility of measurement without atomic clocks. But, as you approach light speed, gamma grows without limit. At 90% of light speed, gamma is about 2.3. Your clock ticks at about 44% of the normal rate. For every second you experience, about 2¼ seconds pass outside. At 99%, gamma is about 7. Your clock ticks at about 14% of normal. At 99.9%, gamma is about 22. Your clock ticks at less than 5% of normal. At 99.99%, gamma exceeds 70. The closer you push toward light speed, the more extreme the effect. The curve rises without bound toward an infinite slowdown at v equals c. An observer moving at 99.999% of the speed of light for what feels to them like a few years could return, to find that thousands of years had passed outside. Time doesn't slow from their perspective. It slows from ours. But the effect is real. The asymmetry in aging is permanent and absolute. This is not theoretical in the abstract sense. It is measured routinely. Muons are subatomic particles produced when high-energy cosmic rays from outside the solar system slam into molecules in the upper atmosphere. They're unstable. They decay radioactively with a half-life of about 2.2 microseconds in the laboratory frame. The atmosphere is about 60 miles thick, and muons are produced at the top. A muon, traveling at 99.5% of the speed of light, should, in a naive calculation, travel only about 0.4 of a mile before decaying. Not 60 miles. The numbers don't work, except that time dilation does work. From the muon's reference frame, its internal clock ticks normally, and it decays after about 2.2 microseconds. But from our reference frame on the ground, the muon's clock is running slow by a factor of about 10. It survives 10 times as long as a non-relativistic muon would, which is long enough to reach sea level. We detect muons at sea level continuously. Every second, hundreds of muons pass through your body. They're harmless at these fluxes. But their presence is confirmation. Time dilation is real. The satellites of the GPS constellation carry atomic clocks accurate to within about 20 nanoseconds. Those satellites are moving at about 2.5 miles per second. From the ground's reference frame, their clocks run slow by about 7 microseconds per day from special relativistic effects. The satellites are also higher in Earth's gravitational field, which causes their clocks to run fast by about 45 microseconds per day from general relativistic effects. The combined correction is about 38 microseconds per day, applied constantly to keep the satellite clocks synchronized with ground clocks. Without those corrections, GPS positioning would drift by several miles every day. The corrections are applied. The system works. The precision of navigation depends on the accuracy of relativistic physics. Every time you get directions on your phone, Einstein's equations are running in the background, making it possible. Connected to time dilation is the effect that makes faster-than-light travel through conventional propulsion permanently impossible. As you accelerate, you don't just experience time differently. You also become progressively more resistant to further acceleration. The effective inertia of a moving object increases with velocity. The same gamma factor governs both time dilation and this increase in effective mass. At 90% of light speed, your effective mass has multiplied by a factor of about 2.3. You need 2.3 times as much force to produce the same acceleration. At 99%, the factor is about 7. At 99.9%, the factor is about 22. At 99.99%, the factor exceeds 70. Each small increment of additional velocity requires more energy than the one before. The rate of increase accelerates toward infinity as you approach the light barrier. To reach exactly the speed of light would require an infinite amount of energy. Not a very large, but finite amount. Infinite. As in, every joule of energy in the observable universe would not be sufficient. The requirement is not hard to meet. It is mathematically impossible to meet. No propulsion system, no matter how efficient, no matter how advanced the civilization operating it, can supply infinite energy. The constraint is not technological. It is mathematical. It follows from the same equations that correctly predict muon lifetimes and GPS drift. There is no workaround within the framework of special relativity. The reason a photon can travel at light speed is that it has no rest mass. That is not a coincidence. It is the key to the entire structure. In special relativity, the relationship between energy, momentum, and mass is given by a precise equation. The square of the total energy equals the sum of the square of the momentum times c squared, plus the square of the rest mass times c to the fourth. For a particle with zero rest mass, the mass term vanishes entirely. The energy equals momentum times c, and a massless particle traveling at exactly c satisfies this equation precisely. Photons are massless. They are constrained to travel at exactly c, not slower, not faster, exactly at c, always. It is their only allowed velocity. An electron has a rest mass of about 9.1 times 10 to the negative 31st kilograms. That non-zero mass means the mass term in the energy equation doesn't vanish. And it means infinite energy would be needed to push it to c. The distinction between zero and any non-zero rest mass is categorical. Zero rest mass must travel at c, always. Any non-zero rest mass can never reach c, ever. The light barrier is not a speed that almost massless particles almost reach. It is an absolute boundary with qualitatively different physics on each side. Photons on one side, everything with mass on the other. So here is the central question. What does physics actually describe on the other side of that boundary? Not how to get there, not the engineering. Just what the equations say about the territory above the speed of light, if such a territory can be said to exist. The Lorentz transformations, the mathematical machinery of special relativity, don't produce an undefined result when you substitute a velocity greater than c. They produce an answer from a regime that looks like a mirror reflection of the familiar physics. And that mirror image is disturbing in a specific and well-understood way. The most immediate consequence concerns causality. If something could carry information from one place to another faster than light, the recipient could receive that information before it was sent. Not as a matter of imprecision or lag. Literally. In certain reference frames, a faster-than-light signal arrives at the destination before it was transmitted from the source. This follows directly from the relativity of simultaneity. Two observers moving relative to each other don't always agree on the order of events separated in space. For events connected by signals slower than light, every observer agrees on the sequence. The cause always precedes the effect. This is guaranteed by the structure of the Lorentz transformations. But for events connected by something faster than light, different observers disagree. And for some observers, the effect precedes the cause. This is not a philosophical puzzle. It is a precise, algebraic consequence. You can calculate, for any superluminal signal between 2 points, the reference frames in which the signal appears to arrive before it was sent. There are always such frames. And in the framework of special relativity, no reference frame is more correct than any other. If causality breaks for one observer, it has broken. There is no absolute frame to appeal to where the right order is restored. The prohibition on faster-than-light signaling is the prohibition on breaking causality. They are the same prohibition. This was formalized in a 1970 paper by Gregory Benford, David Book, and William Newcomb. They described what became known as the tachyonic antitelephone. The thought experiment goes like this. Suppose you have a device that can transmit messages faster than light. You use it to send a message to a receiving station that is moving away from you at some velocity. Due to the relativity of simultaneity, the receiving station, in its own reference frame, receives your message before you sent it. The station, interpreting the message as expected, immediately uses its own faster-than-light transmitter to reply. The reply travels back to you. It arrives in your reference frame before you transmitted the original message. You hold the reply in your hands before the original question was asked. You read the reply. Then you choose not to send the original message, which means the station has no message to receive, which means there is no reply, which means you don't receive the reply, which means nothing stops you from sending the message, which means the reply arrives. A closed loop with no consistent resolution. Not merely a strange situation. A logical contradiction. A physical system that simultaneously happened and didn't happen. The tachyonic antitelephone is not an engineering problem. It is a logical problem. It shows that faster-than-light signaling, combined with the relativity of simultaneity, produces a universe that is logically inconsistent. And we live in a consistent universe. Its past happened one way. Its physical laws don't contradict themselves. The only resolution is that faster-than-light signaling is impossible. Despite this, the concept of a faster-than-light particle was worked out rigorously in the 1960s. The particle was called a tachyon, from the Greek word for swift. Gerald Feinberg, a physicist at Columbia University, published the foundational paper in 1967 in the journal Physical Review. Feinberg's approach was careful and precise. Special relativity, he noted, doesn't explicitly forbid particles that always travel faster than light. It forbids accelerating anything with positive mass through the light barrier. But the equations have a third regime. Below the barrier, particles with positive real rest mass, always subluminal. At the barrier, massless particles, traveling exactly at c. Above the barrier, hypothetical particles that are always superluminal, that cannot slow down to c, just as ordinary particles cannot speed up to it. Feinberg called the particles in the third regime tachyons and worked out their properties. What he found was precise and strange. In special relativity, the energy-momentum-mass relationship involves the rest mass as a squared quantity. For ordinary particles, rest mass squared is positive. For photons, it's 0. For tachyons, Feinberg proposed, it would be negative. A particle with a negative value for mass squared has what mathematicians call an imaginary mass. Imaginary in the technical sense, meaning expressible as a real number times the square root of -1. Not fictional, not absent, but measured in imaginary units. And the physical consequences of imaginary mass in the relativistic framework are precisely inverted from real mass. For an ordinary particle, adding energy increases velocity, approaching c from below. For a tachyon, adding energy decreases velocity, approaching c from above. For an ordinary particle, at 0 kinetic energy, the particle is at rest. For a tachyon, at 0 energy, the particle is moving at infinite speed. The entire energy-velocity relationship is the mirror image of ordinary matter, reflected through the light barrier. A tachyon, with very little energy, moves extremely fast. A tachyon, with a lot of energy, slows down towards C but never reaches it. Removing energy from a tachyon makes it move faster. Adding energy makes it move slower. The universe above the light barrier, in Feinberg's formalism, is governed by physics that runs backward relative to what we know. Different reference frames disagree about the direction a tachyon travels in time. In one frame, the tachyon travels from point A to point B. In another frame, moving in a certain direction relative to the first, the tachyon appears to travel from B to A. The source becomes the receiver. The receiver becomes the source. The arrow of causation flips depending on who's watching. This is the formal, mathematical expression of the causality violation. It isn't a paradox you can avoid by being careful about how you set up the experiment. It is inherent in the Lorentz transformation properties of superluminal trajectories. Any superluminal trajectory, under some Lorentz boost, appears to run backward in time. And since there's no preferred reference frame, there's no saying which direction is the real one. The tachyon's causal arrow is not just ambiguous, it is undefined. Searches for tachyons in particle physics have found nothing. Extensive experiments at accelerators, including those at CERN, Fermilab, and other major facilities, have looked for particles with the properties Feinberg described. No such particle has been detected. If tachyons exist in nature, they interact with ordinary matter so weakly that they leave no trace in any detector ever built. The experimental record over more than half a century is a complete, null result. But Feinberg's theoretical framework had a more lasting impact than its null experimental result might suggest. The concept of a particle with imaginary mass migrated into quantum field theory, where it acquired an entirely different and crucially important meaning. In quantum field theory, particles are excitations of fields. Every type of particle corresponds to a quantum field that permeates all of space. Electrons arise from the electron field. Photons arise from the electromagnetic field. Quarks arise from quark fields. The properties of particles, including their masses, are encoded in the structure of these fields and their interactions. The mass of a particle is related to the curvature of the field's potential energy landscape. If you imagine the potential energy as the shape of a bowl, particles are ripples in the field around the bottom of the bowl. The steeper the bowl, the higher the mass. A flat-bottomed bowl gives massless particles. An inverted bowl, a hilltop, gives a negative curvature. And negative curvature, in the field theory sense, means negative mass squared. That's the tachyonic condition. A field, in a tachyonic state, is sitting at an unstable maximum of its potential energy. Any perturbation will cause it to roll away from the maximum and toward the true minimum of the potential. The tachyon is not a particle flying around faster than light. It is a diagnostic, an indicator that the field is in an unstable configuration and is about to transition to something more stable. The word has been completely repurposed. In modern usage, a tachyonic field is an unstable field. A tachyonic instability drives a phase transition. The faster-than-light sense belongs to the 1960s. The field instability sense is what physicists mean today. The most important tachyonic instability in nature is associated with the Higgs field. The Higgs field permeates all of space. In the hot, symmetric state of the very early universe, the Higgs field sat at an unstable maximum of its potential energy. Its ground state, the configuration of lowest energy, was tachyonic. As the universe cooled below a critical temperature, the Higgs field spontaneously transitioned to the true minimum of its potential. This process is called the electroweak phase transition, and its consequences for the structure of the universe were total. Before the transition, the Higgs field was at the unstable maximum. The particles that interact with the Higgs were all massless. The electromagnetic force and the weak nuclear force were unified into a single electroweak force. After the transition, the Higgs field settled into the true minimum. The symmetry that unified electromagnetism and the weak force was broken. The W and Z bosons, the carriers of the weak force, acquired mass through their coupling to the non-zero Higgs field. The fundamental fermions, the electrons and quarks that make up all matter, also acquired mass. The separation between electromagnetism and the weak force became permanent. The mass structure of the observable universe was set. The fact that electrons have mass, that atoms have definite sizes, that hydrogen bonds form, that chemistry exists, that you are made of structured matter rather than dispersed massless particles. All of it traces back to the Higgs field's tachyonic instability, driving it from the hilltop to the valley. The Higgs boson, detected at the Large Hadron Collider in 2012 after a search that took decades, is the particle that arises from oscillations of the Higgs field around that stable minimum. It is the ripple in the valley where the tachyon once drove the system. The tachyon did its work and left a transformed vacuum behind. We live in the aftermath. String theory provides another context where tachyons appear as indicators of incompleteness rather than physical particles. The original bosonic string theory, the simplest version of string theory developed in the late 1960s and early 1970s, had a tachyonic ground state. The lowest energy configuration of the open string, the fundamental excitation mode of the theory, had imaginary mass. This was immediately recognized as a problem. A tachyonic ground state means the vacuum of the theory is unstable. The theory was sitting at a potential maximum. It was not describing the true ground state of whatever physical reality it was meant to represent. The resolution came through extending the theory to include supersymmetry, a symmetry that pairs bosons with fermions. In supersymmetric string theories, called superstring theories, the tachyonic ground state disappears. The true ground state becomes stable. The mass squared is zero or positive. The theory sits in a genuine valley rather than on a hilltop. This is one of the reasons superstring theories attracted serious attention. Not only did they offer a more natural unification of gravity with quantum mechanics, but they solved the tachyon problem of the simpler bosonic theory by providing a stable vacuum. Whether any superstring theory correctly describes our universe is an unresolved question. But the structure of the argument shows how tachyons function in the landscape of theoretical physics. They appear where theories are incomplete. They point toward more complete descriptions. They drive transitions to better understood ground states. And in none of these contexts do they have anything to do with physical particles racing through space at superluminal velocities. Set all of this aside now, because there's another path into the question of what lies beyond the light barrier. Not through imaginary mass particles, but through the geometry of spacetime itself. General relativity, Einstein's theory of gravity from 1915, treats gravity not as a force transmitted through space, but as the curvature of spacetime produced by mass and energy. massive objects warp the fabric of space-time around them. Other objects follow the straightest possible paths through that curved fabric. What we experience as the gravitational force pulling us toward the Earth's center is us following the straightest possible trajectory through the curved space-time near a massive planet. The geometry tells matter how to move, and the geometry of space-time is governed by Einstein's field equations, 10 coupled non-linear differential equations that relate the distribution of mass and energy to the curvature of space-time. These equations have many solutions. The Schwarzschild solution describes a non-rotating black hole. The Kerr solution describes a rotating black hole. The Friedmann-Lemaitre-Robertson-Walker solutions describe the expanding universe. And there are more exotic solutions. Solutions that describe structures with no obvious physical realization, but complete mathematical validity. Some of those exotic solutions describe what might be called shortcuts through space-time. Einstein and Nathan Rosen identified one category of exotic solution in 1935. Working with the geometry of the Schwarzschild black hole, they found that the mathematics of the black hole interior, analyzed through different coordinate systems, connects to another region of space-time. Not to the same exterior region the black hole came from, but to a second exterior region, mathematically equivalent to the first, but separate from it. The bridge between these two exterior regions became known as the Einstein-Rosen bridge. It looked, in the coordinate diagrams, like a tunnel, a topological connection between two distinct regions of the universe, possibly separated by vast distances or possibly corresponding to entirely different universes. Early analysis showed that the Einstein-Rosen bridge was not traversable. It collapsed too quickly. The geometry of the bridge was dynamic, evolving in time, and the throat pinched off before any signal or physical object could complete the transit. Additionally, any object approaching the bridge from the Schwarzschild exterior would cross the event horizon and then face the singularity before reaching the bridge. The tidal forces near the singularity would be lethal. The Einstein-Rosen bridge was a mathematical structure, not a travel mechanism. For over 50 years, it stayed in the curiosity column. Then, in 1988, the situation changed. Kip Thorne, then at Caltech, published a paper with Michael Morris and Ulvi Yurtsever that took the question seriously in a way it hadn't been before. The paper, titled Wormholes in Spacetime and Their Use for Interstellar Travel, appeared in Physical Review Letters. Its origin was unusual. Carl Sagan was writing his science fiction novel, Contact, and he needed a physically plausible mechanism for his protagonist to cross interstellar distances in a short time. He asked Thorne whether general relativity permitted any such mechanism. Thorne, rather than dismissing the question, investigated it carefully. His team worked through the conditions required for a traversable wormhole, one that had no singularity at the throat, one whose tidal forces were survivable, one whose throat remained open long enough for transit. The result was that traversable wormholes were mathematically consistent solutions to Einstein's equations. A spacecraft could enter one mouth of the wormhole, travel through a relatively short throat, and emerge from the exit potentially light years away. The journey through the throat could take minutes or hours. The two mouths could in principle be positioned anywhere in the universe, separated by any distance. An outside observer watching the journey would see the spacecraft disappear into one mouth and reappear from the other, in a time far shorter than light, would need to travel the same distance through normal space. The physics inside the wormhole respects the local speed limit. Photons in the throat still move at c through their local geometry. But the shortcut makes the effective transit time much less than the time required for a photon to take the long way around. From the outside, the trip appears faster than light could manage without the shortcut. Traversable wormholes came with a condition that immediately placed them in the same category as the Alcubierre warp drive. To hold the throat open against the natural tendency of the geometry to collapse, the wormhole required material at the throat with negative energy density. Exotic matter. The same substance that appears in every serious proposal for superluminal shortcuts through spacetime. Negative energy. Understood as a region of space with less energy than the vacuum, less than nothing in the classical sense. The Casimir effect produces something in this category. Between two closely spaced conducting plates, the restriction on quantum vacuum fluctuations creates a region of reduced energy density, technically below the vacuum value. It's been measured. The effect is real, but the amounts of negative energy the Casimir effect produces are extraordinarily small, and the amounts needed to stabilize a wormhole of any useful size are vastly larger. The quantum energy inequalities, rigorous theorems proved by Lawrence Ford and Thomas Roman and extended by subsequent researchers, establish strict bounds on how much negative energy quantum fields can produce in any region and for how long. The magnitude of the allowed negative energy scales inversely with the size and duration of the region. For regions large enough and long-lived enough to serve as wormhole throats, the quantum energy inequalities allow so little negative energy that no physically reasonable configuration of quantum fields could provide what's required. The Casimir effect is real. What it produces is real. But calling it a step toward a traversable wormhole is like calling a candle a step toward powering a city. The category might be the same. The scale is not in the same universe. The warp drive is worth careful treatment on its own terms. In 1994, Miguel Alcubierre, a young Mexican physicist doing postdoctoral work at the University of Wales in Cardiff, published a paper in Classical and Quantum Gravity titled The Warp Drive: Hyperfast Travel Within General Relativity. The paper opened a conversation that is still ongoing 30 years later. Alcubierre was not the first person to wonder about faster-than-light travel, but he was the first person to construct a mathematically precise solution to Einstein's equations, describing a space-time geometry in which a region could translate faster than light, while the contents of that region remained in locally flat space-time. The key distinction is between moving through space and being carried by space. Einstein's speed limit applies to things moving through space-time. It says nothing about the motion of space-time itself. And there's observational evidence that space-time can move faster than light. The universe is expanding. Galaxies far enough away from us are receding faster than c. Not because they're moving through space at superluminal velocities, because the space between us and them is expanding. Each small increment of distance is growing. Add them up over cosmic scales, and the recession velocity exceeds c. General relativity accommodates this without contradiction, because no local violation of the speed limit occurs. No signal passes between the galaxy and us faster than light. The galaxy is simply being carried away by the expansion of the fabric. And there's no upper limit in general relativity on the rate at which the fabric can expand. Alcubierre asked whether this freedom could be exploited locally. Whether you could engineer a region of spacetime that contracted ahead of a spacecraft and expanded behind it, carrying the craft forward at any speed, while the craft itself sat in perfectly flat, normal spacetime. The answer, in the mathematics, is yes. He constructed the metric for such a configuration. Inside the bubble, flat spacetime, normal physics. No forces on the crew. Outside, the surrounding universe, also flat, far from the bubble. At the boundary, the warping shell, where the geometry transitions from contracting at the front to expanding at the rear. The entire bubble translates through the universe at any chosen speed. The crew experiences nothing unusual. No acceleration. No relativistic effects. No time dilation different from what the outside universe experiences. The math checks out. The metric is a valid solution to Einstein's field equations. And the physics community acknowledged this immediately. Alcubierre hadn't made an error. He'd found a genuine loophole in the geometry. But what the bubble required to work brought the familiar obstacle. The warping shell at the boundary, where space-time transitions from contracting at the front to expanding behind, had to be filled with material with negative energy density. Exotic matter. The early calculations of the required amount were extreme. Some estimates placed the needed negative energy at a quantity comparable to the total mass energy of Jupiter, expressed as negative. Other early estimates were even worse. The precise number depended on the details of the metric, but all early results were clearly impossible. The mathematics was right. The engineering was not merely difficult. It required a substance that, as far as anyone knew, didn't exist. The Alcubierre drive joined the Einstein-Rosen bridge in the curiosity column. Interesting physics. No connection to anything buildable. What kept the research alive were subsequent reductions in the energy requirement. In 1999, Chris van den Broek at the Free University of Brussels found a modification that dramatically reduced the exotic matter requirement. In general relativity, a geometric region's exterior size and interior size don't have to match. You can have a small exterior enclosing a large interior through curved geometry. This is allowed by the mathematics and has no counterpart in flat space. Van den Broek proposed keeping the bubble's exterior surface very small, which reduced the amount of exotic matter needed in the shell while maintaining a spacious interior for the spacecraft. By shrinking the exterior to macroscopic but small scales while keeping the interior large, the exotic matter requirement dropped by many orders of magnitude. Still impossible to produce, but a fundamentally different scale of impossible. Harold White at NASA's Johnson Space Center refined the geometry further in the 2010s by replacing the spherical bubble with a toroidal, ring-shaped configuration and distributing the exotic matter around the torus. White's calculations suggested the requirement could be reduced to roughly 700 kilograms. 700 kilograms of exotic matter with negative energy density, a number that fits in a room. Not achievable. The substance doesn't exist in any producible form. But 700 kilograms is categorically different from the mass of Jupiter. The problem had evolved from requires more than the observable universe contains to requires a substance that doesn't exist in any amount we know how to make. The ceiling had changed, even if it was still out of reach. In 2021, Alexei Bobrik and Gianni Martier published what became the most systematic treatment of warp drive physics to date. Rather than analyzing individual designs one at a time, they constructed a general mathematical framework applicable to any warp drive configuration. Their analysis showed that every warp drive can be decomposed into three regions: an exterior of flat spacetime, an interior of flat spacetime where the passengers travel, a warping shell between the two, where the geometry transitions from the exterior to the interior. The differences between warp drive designs come down entirely to the properties of the shell. What material fills it? How the geometry curves through it? How thick it is? What energy conditions the material satisfies? By mapping this design space systematically, Bobrik and Martiret identified regions that previous research had missed. The most significant finding was about subluminal warp drives. Warp bubbles moving below the speed of light can, in principle, satisfy the classical energy conditions. They can be filled with ordinary matter, matter with positive energy density, no exotic matter required. A subluminal warp bubble doesn't cross the light barrier. It can't get you to a distant star faster than light could, but it can carry passengers at high fractions of the speed of light with no internal forces whatsoever. No crushing acceleration, no physiological stress from g-forces. And the physics to build such a drive, while far beyond current capability, doesn't require a substance that might not exist. The Bobrik-Martiret framework also came with a computational tool called Warp Factory, which lets researchers numerically evaluate any specific warp drive proposal, compute the required matter distributions, check energy condition satisfaction, and test stability. This turned warp drive research from a collection of individual analytical papers into something with the infrastructure of a proper scientific field. The ability to systematically evaluate designs is what a mature research program looks like. The field, in 2 decades, had matured from a single 8-page curiosity into an organized research program with frameworks, numerical tools, and systematic results. That doesn't mean a warp drive is coming, but it means the field is being taken seriously in the right way. Even if the exotic matter problem was somehow solved, superluminal warp travel faces additional obstacles that arise not from material science, but from fundamental physics. The event horizon problem is among the most serious. When a warp bubble moves faster than light, the leading edge of the bubble advances superluminally. No signal originating from inside the bubble can travel fast enough to reach the leading edge. The front wall is outrunning any communication that the interior can send forward. This creates an event horizon at the bubble's leading face, a causal boundary, a surface beyond which the interior has no ability to influence what happens. This is the same mathematical structure as the event horizon of a black hole. The consequences for navigation are severe. A pilot inside a superluminal warp bubble cannot steer the bubble. Any navigation command, any signal sent toward the front to adjust the bubble's trajectory can never reach the bubble's boundary. The command chases the leading edge forever and never arrives. Any course correction is impossible during the voyage. Any obstacle detected in the path ahead cannot be communicated to the steering system. The bubble follows its initial trajectory rigidly, unable to respond to anything it encounters. Additionally, the bubble cannot be stopped from inside. To decelerate or halt, you need to modify the exotic matter distribution in the bubble's shell. That requires signals from inside to reach the shell. For a superluminal bubble, those signals can't reach the leading edge of the shell. The crew is locked in. The voyage runs its course on the initial trajectory until either the ship arrives at its pre-programmed destination or external infrastructure previously positioned at the destination collapses. Bubble from outside. The pilot is a passenger in the most absolute sense. They have no control whatsoever over the vehicle they're traveling in. The Hawking radiation problem adds another layer. Event horizons, any event horizon, emit thermal radiation through a quantum mechanical process first described by Stephen Hawking in 1974. At the boundary of an event horizon, virtual particle-antiparticle pairs spontaneously form from the quantum vacuum. In ordinary flat space, these pairs annihilate almost immediately and leave no net effect. But near an event horizon, the horizon can intervene. One member of the pair falls inward across the horizon before the pair can annihilate. The other escapes outward. From outside the horizon, this looks like thermal radiation being emitted by the horizon itself. The temperature of the radiation is proportional to the surface gravity at the horizon. For stellar mass and larger black holes, the temperature is far too low to be significant. But for smaller, lighter objects, or for differently structured horizons, the temperature rises. The event horizon at the leading edge of a superluminal warp bubble generates Hawking radiation. Unlike the Hawking radiation from a conventional black hole, which radiates in all directions, the geometry of the moving warp bubble focuses this radiation inward, toward the interior of the bubble, toward the crew. The calculations on the intensity are not fully settled. They depend on the specific bubble geometry and on details of quantum field behavior near moving horizons. But the mechanism is standard physics. The horizon exists. Horizons radiate. The radiation in a warp bubble is directed at the passengers. This is not an engineering challenge to be solved with better shielding. It is built into the quantum structure of the event horizon that a superluminal bubble necessarily creates. A subluminal bubble, which moves slower than light, does not generate a leading-edge event horizon. It doesn't have this problem. But a subluminal bubble, as already noted, doesn't cross the light barrier either. The problems associated with superluminal travel appear to be inseparable from what makes it superluminal. They are features of the physics, not engineering deficiencies. The particle accumulation problem completes the picture. Interstellar space is not a perfect vacuum. It contains roughly one hydrogen atom per cubic centimeter on average, plus trace amounts of other elements, dust grains, stray electrons, ions, cosmic rays. For conventional spacecraft, this dilute medium is negligible. For a superluminal warp bubble, the interaction physics changes dramatically. As the bubble advances, particles at the leading edge get trapped in the compressed geometry of the bubble's front wall. The compression accelerates these particles to high energies. They don't escape from the front of the bubble. They accumulate in the leading wall, building up over the course of the voyage. A journey of several light-years sweeps through vast numbers of hydrogen atoms, each gaining energy from the interaction with the bubble's geometry. When the bubble reaches its destination and shuts down, all of this accumulated energy is released at once. The particles burst outward in a concentrated beam aimed in the direction the ship was traveling. The energy content of that beam, calculated from the properties of the interstellar medium and the bubble's velocity, could be catastrophic for anything in its path. The ship, inside the bubble throughout, is unharmed. Whatever is at the destination is not. A superluminal warp ship arriving at a distant star system would emit a devastating directed beam of high-energy particles aimed directly at that system, not as an accidental side effect of a rare malfunction, as an inevitable consequence of the standard physics of bubble interstellar medium interaction. Any realistic superluminal warp mission would require extensive deceleration phases in empty space. Far from the destination, careful aiming of the exit beam away from inhabited or scientifically valuable regions, and probably advance warning to the destination system. This complexity piles on top of the exotic matter requirement, the horizon problem, and the Hawking radiation. None of these obstacles is hypothetical. They are consequences of well-understood physics applied to the warp bubble geometry. The universe has, in effect, erected a defense in depth against superluminal geometric shortcuts. Multiple independent obstacles, each rooted in a different branch of physics, all pointing at the same destination. Superluminal travel is not merely technically impossible, it appears to be actively resisted by the structure of the laws of physics themselves. Quantum field theory adds its own formal prohibition through a property called microcausality. In quantum field theory, physical observables are represented by operators. The requirement of microcausality states that any two operators describing measurements at space-like separated points in spacetime must commute with each other. Commuting operators mean that measuring one doesn't influence the other. No information passes between space-like separated measurements. This is the formal mathematical statement that quantum field theory cannot transmit information faster than light. Microcausality is not a physical assumption imposed from outside. It is a mathematical condition that quantum field theories must satisfy to be consistent with special relativity. Every quantum field theory used in modern physics, including quantum electrodynamics, quantum chromodynamics, and the electroweak theory that together constitute the standard model of particle physics, satisfies microcausality. The standard model predictions match experimental data to extraordinary precision. Quantum electrodynamics, the theory of electrons and photons, matches measurements of the electron magnetic moment to better than 1 part in a trillion. That is the most precisely confirmed prediction in the history of science. If microcausality were violated, the standard model would fail. It doesn't fail. Microcausality holds. Causal locality is built into the deepest confirmed theory of nature. Quantum entanglement is the phenomenon most commonly invoked as a potential exception, and it's worth being precise about why it isn't. Entanglement is real. When two particles are entangled, measuring one determines the state of the other instantly, regardless of the distance separating them. This has been confirmed in experiments spanning distances from centimeters to thousands of miles, using satellites to distribute entangled photon pairs. The correlations are instantaneous. This looks like faster-than-light communication. Here is why it isn't. When you measure your entangled particle, you get a random result. The outcome is governed by the quantum state of the pair and the quantum mechanical probability rules, but you cannot predict or control the specific outcome you'll get before measuring. Your partner, measuring the other particle anywhere else in the universe, also gets a random result they cannot control. The results are correlated. But each person, looking only at their own result, sees a random sequence, indistinguishable from noise. The correlation between the sequences is only visible when you bring both datasets together and compare them. Bringing those datasets together requires conventional communication. A phone call, a transmission, something that travels at or below the speed of light. You cannot encode a message in your partner's random results before they've measured anything. You cannot choose what result they'll get. The information about the correlation is classically distributed. The entanglement provides the correlation. It cannot provide the context needed to extract information from that correlation. And correlation without context is indistinguishable from noise. This result is known as the no communication theorem. It was first proved by Philippe Eberhard in 1978 and has been strengthened and extended since. It is a mathematical theorem, not a conjecture. It establishes that quantum mechanics, including quantum entanglement in all its forms, cannot transmit information faster than light. No experimental violation has ever been found. No theoretical loophole has survived careful scrutiny. The no communication theorem is as solid as theorems in physics get. Entanglement is strange. It implies non-local correlations that no classical model can reproduce. Bell's theorem proves this. The violations of Bell inequalities confirmed in experiments by Clauser, Aspect, Zeilinger, and many others establish that the correlations cannot be explained by any local hidden variable theory. Something genuinely non-local is present at the quantum level. But that non-local something cannot be used to send a message. The universe arranged things so that quantum mechanics is locally causal, even though it is globally non-local in a statistical sense. It is strange. It is not an exploit. The energy condition theorems provide a different angle of the same prohibition. These are mathematical theorems in general relativity about the behavior of spacetime in the presence of matter and energy, satisfying various conditions. The weak energy condition requires that the energy density seen by any observer in any reference frame is non-negative. The null energy condition requires the same for observers moving at the speed of light. The average null energy condition is weaker, requiring that the average of the energy density along any complete null geodesic, a light ray, is non-negative. Topological censorship theorems, proved by John Friedman, Kristin Schleich, and Donald Witt in the 1990s, establish that in any spacetime satisfying the averaged null energy condition, no shortcut can be traversed. More precisely, any causal curve that enters and exits a wormhole mouth can be continuously deformed to a curve that doesn't enter the wormhole. The shortcut is topologically trivial. Traversable wormholes require violations of the averaged null energy condition. Traversable superluminal warp bubbles also require such violations. This is the formal sense in which exotic matter is required. Not just difficult to produce, required by the topology of the geometry. The quantum energy inequalities narrow the available violations to amounts far below what any useful shortcut needs. Between the topological censorship theorems and the quantum energy inequalities, the geometry of spacetime appears to be fundamentally and rigorously closed against superluminal shortcuts, at least within the framework of semi-classical gravity, quantum field theory on a classical curved background. Whether quantum gravity changes, this conclusion is unknown. The semi-classical framework has known limitations near the Planck scale. A complete theory of quantum gravity might modify the energy conditions in ways that open possibilities the current framework forecloses. Or it might close them further. That is the genuine uncertainty. The question of what quantum gravity says about all of this is the deepest and most honest open issue in this subject. General relativity and quantum mechanics are the two most experimentally successful theories in physics. Both are precise, both are confirmed to extraordinary accuracy in their domains. They are also deeply incompatible. General relativity treats spacetime as a smooth, continuous, geometric manifold. Quantum mechanics is built on discrete states, probability amplitudes, and a quantization procedure that produces energy levels in steps. When you try to apply quantum mechanics to the gravitational field directly, you get a theory that produces nonsensical infinities in calculations. The infinities appear at short distances near the Planck length. The Planck length is roughly 1.6 times 10 to the negative 35th meters. A proton is already roughly 10 to the negative 15th meters, already far beyond direct visualization. The Planck scale is about 20 orders of magnitude smaller than that. It is where the smooth geometry of general relativity breaks down, and where quantum effects on the structure of spacetime become important. Every serious approach to quantum gravity predicts that spacetime has structure at the Planck scale that is not present in the smooth continuum of classical general relativity. Loop quantum gravity describes spacetime as built from discrete loops and networks. Area and volume become quantized, taking discrete minimum values. The smooth manifold of classical spacetime emerges as an approximation valid at scales much larger than the Planck length. String theory describes a spacetime where the strings themselves have an intrinsic length comparable to the Planck scale. At distances much smaller than the string length, the concept of space and time as a classical manifold breaks down. Causal dynamical triangulations build spacetime from discrete, simplicial building blocks and study which configurations emerge at large scales. In all of these frameworks, the causal structure of spacetime, the ordering of events into past, present, and future, the light cone that separates causal from acausal influences emerges from the discrete quantum geometry at the Planck scale. It is not imposed as an external rule. It is a property of the quantum spacetime fabric itself. In this picture, the speed of light is not a speed limit chosen by nature and attached to spacetime from outside. It is the natural maximum propagation speed of correlations through the quantum gravitational network that constitutes spacetime. The way the speed of sound in a material is determined by the material's properties. You cannot send sound through a material faster than its natural wave propagation speed by pushing harder. The material's structure determines the maximum. If spacetime is a discrete quantum network, c is the network's maximum propagation speed. Exceeding it would not be extremely difficult. It would be structurally undefined. Like asking a sound wave to travel faster than the speed of sound in the medium it's traveling through. The concept doesn't apply. The structure prevents it. This picture is consistent with everything we observe. It explains why the speed of light appears in the equations of electromagnetism, gravity, and quantum mechanics. It explains why the causal structure of spacetime is the same for all observers. It explains why every measurement ever made confirms Lorentz invariance, the symmetry of special relativity. But it is not confirmed in the sense of being directly tested at the Planck scale. The Planck scale is beyond any conceivable experiment with known technology by an enormous margin. The Large Hadron Collider reaches energies of several tera-electron volts. The Planck energy is about 1.2 times 10 to the 19th giga-electron volts, roughly 16 orders of magnitude above the LHC. 16 orders of magnitude is a factor of 10 million billion. We are not close to probing the Planck regime. We may never be. The discrete structure of spacetime, if it exists, is inferred from theoretical consistency and not directly measured. And so the deepest version of the question, whether the light barrier is a structural property of quantum spacetime that is definitively unbreakable, remains genuinely open, not answerable by any measurement we can currently make, but also not arbitrary. The case for it is strong. The case against it is speculation. And in physics, strong cases without direct experimental confirmation are exactly where the frontier is. What science currently thinks happens beyond light speed is therefore not a single answer. It is a layered structure of conclusions, each grounded in a different framework, all converging on the same result. At the first layer, special relativity, nothing with mass can reach the speed of light through any conventional propulsion mechanism. The mathematics is airtight. A century of experiment has found no exception. This layer is settled. At the second layer, formal mathematics, the Lorentz transformations describe a mirror regime above the light barrier, where particles have imaginary mass and the energy-speed relationship is inverted. This regime is mathematically coherent and physically empty. No tachyon has been detected. The causality arguments make their existence logically problematic. In modern physics, the tachyon concept has been repurposed to mean field instability, which is important and real and has nothing to do with faster-than-light particles. At the third layer, causality, faster-than-light information transfer, is inconsistent with the structure of the universe. The tachyonic antitelephone makes this explicit. The no-communication theorem in quantum mechanics confirms it. Microcausality in quantum field theory enforces it mathematically. The energy condition theorems in general relativity constrain the geometric loopholes. The universe consistently prevents effects from preceding causes across every framework, in every experiment. At the fourth layer, spacetime geometry, a mathematical loophole exists in warp drives and wormholes. The loophole is real in the mathematics. It is blocked in the physics by the requirement for exotic matter with negative energy density, by the quantum energy inequalities that restrict negative energy production, by the event horizon problem that removes navigational control, by the particle accumulation problem, and by the Hawking radiation. The subluminal versions of warp drives are potentially buildable from ordinary matter, which is genuine progress, and they avoid the causality problems of superluminal versions. At the fifth layer, quantum gravity, the causal structure of space-time may be a fundamental property of the discrete quantum geometry at the Planck scale. If so, the speed of light is not a limit imposed on space-time, but a property of space-time. This layer is theoretically motivated and experimentally inaccessible. These 5 layers are not 5 versions of the same argument. They are 5 independent lines of reasoning from different frameworks, converging on the same conclusion. The relationship between the speed of light and the structure of electricity and magnetism is something most discussions of the light barrier overlook. But it is actually where the story starts. James Clerk Maxwell, a Scottish physicist working in the 1860s, unified the previously separate theories of electricity and magnetism into a single mathematical framework. His 4 equations described how electric and magnetic fields are generated, how they change in time, and how they interact with each other. When Maxwell solved his own equations, he found that they predicted the existence of electromagnetic waves, oscillating electric and magnetic fields propagating through space. He calculated the speed at which these waves would travel. The answer, derived purely from the equations of electricity and magnetism, was approximately 186,282 miles per second. Maxwell immediately recognized this. He had just derived the speed of light from first principles. He hadn't assumed anything about light. He had started from the equations of electricity and magnetism, measured quantities that could be determined from tabletop experiments with wires and magnets, and arrived at the speed at which light had been experimentally measured to travel. The conclusion was inescapable. Light is an electromagnetic wave. The electric and magnetic properties of the vacuum determine how fast electromagnetic waves travel. The speed of light is therefore not an arbitrary number chosen by nature. It is the speed at which disturbances in electric and magnetic fields propagate through empty space. It is determined by two fundamental constants, the permittivity of free space and the permeability of free space, which describe how easily electric and magnetic fields form in a vacuum. Combine those two constants and you get 1 over the square root of their product, which equals c. The speed of light fell out of the equations of electromagnetism as an automatic consequence of how the vacuum responds to electromagnetic fields. This is what Einstein was protecting when he built special relativity around the constancy of c, not just the speed of light. The speed of electromagnetic interaction, the rate at which electric and magnetic fields can influence each other and propagate their changes through space. Now consider what it means for c to appear in Einstein's famous equation relating mass and energy. E equals mc squared. The speed of light, appearing as a squared factor, relates mass to energy. But why should the speed of electromagnetic waves appear in an equation about mass? The answer reveals something deep about the structure of physics. In the framework of special relativity, the speed of light is not primarily the speed of a specific type of wave. It is the conversion factor between spatial intervals and temporal intervals in the geometry of spacetime. Spacetime is a four-dimensional geometric structure. 3 dimensions of space and 1 of time, woven together into a unified fabric. Distances in spacetime involve both spatial and temporal components. To convert between them, you need a conversion factor that has units of speed. That factor is c. It is the rate at which the universe converts spatial distance into temporal distance, or, equivalently, the rate at which time and space interconvert in the geometric structure of the cosmos. Light travels at c not because light is special in some way that other things are not. Light travels at c because photons are massless, and massless particles propagate at the characteristic speed of the space-time metric. If you could somehow strip the rest mass from an electron, it would also travel at c. It would become massless, like a photon. The constraint runs at the level of the geometry, not at the level of the particle type. C is the geometric rate. Everything without mass rides at that rate. Everything with mass moves slower, with the energy cost of acceleration diverging to infinity as you approach the geometric rate. The equation E equals mc squared says that mass is equivalent to energy, separated only by a unit conversion involving the fundamental geometric scale of the universe. Rest mass is condensed spacetime energy. The c² is the exchange rate between the two. And the exchange rate is determined by the geometry of the cosmos, not by the properties of any particular particle. This framing clarifies something important about what it would mean to exceed the speed of light. It would not be traveling faster than electromagnetic waves happen to travel. It would be moving faster than the characteristic speed of the spacetime metric, faster than the rate at which the geometric structure of the universe propagates, changes, and influences. In a discrete quantum spacetime picture, it would be propagating correlations faster than the network that constitutes spacetime allows. Not just difficult, not even just energetically impossible. Structurally undefined in the way that a temperature below absolute zero is undefined. Absolute zero is the temperature at which all thermal motion ceases. You cannot go below it because there is nothing left to remove. It is the floor of the concept. Light speed may be the corresponding ceiling, not a limit on a continuous range of speeds that extends above it. The boundary of the concept of speed itself, where the geometry of spacetime changes character in a way that makes moving faster undefined. The relationship between light speed and information is another angle on the same deep structure. Information is physical. This statement, which sounds philosophical, has a rigorous meaning in physics. Information must be encoded in physical states. It must be transmitted by physical processes. It must be stored in physical systems. And because information is physical, its transmission is subject to physical laws. In particular, information cannot travel faster than the maximum rate at which physical influences propagate, which is c. This connection between information and the light barrier is formalized in what physicists call causality, the principle that information can only flow from cause to effect, from past to future, never in the reverse direction. Causality requires a well-defined time ordering. A well-defined time ordering requires that the same ordering holds for all observers. And the same ordering holds for all observers only if the influences connecting events travel at or below c. The speed of light is therefore not just the speed of a particular kind of wave. It is the maximum rate of information transfer in the universe, the rate at which one physical event can influence another, the rate at which the present moment can affect the future. And the reason it is the maximum is that c is the characteristic speed of the geometry of spacetime, the speed at which the geometry itself propagates, changes. If anything traveled faster than c, it would influence events before the geometry of spacetime had propagated the connection between those events. It would be acting on a stage whose curtain hadn't been drawn yet. In a universe governed by laws, by regularities, by the consistent connection of causes to effects, this cannot be allowed. And so, the universe does not allow it. One of the most productive ways to think about the light barrier is to ask what would have to be different about the universe for it not to exist. Suppose, hypothetically, that the speed of light were not a universal limit. Suppose instead that it were just a very fast speed, beyond which you had to work harder to accelerate, but which was not formally infinite to reach. In such a universe, Lorentz invariance would be broken at high velocities. The relativity of simultaneity would break down. Absolute time would be restored. The electromagnetic equations would need to be modified. The deep connection between electricity, magnetism, and light would need to be severed. The Higgs mechanism, which relies on quantum field theory built on Lorentz invariance, would need to be revised. The stability of ordinary matter, which depends on quantum mechanical processes that respect Lorentz symmetry, would need to be re-examined. The predictions of the standard model of particle physics, all of which depend on Lorentz invariance, would fail. And all of those predictions are confirmed experimentally to extraordinary precision. Breaking the light barrier is not like relaxing a traffic law. It is like removing a load-bearing wall from a building. The entire structure of known physics is built on the invariance of the speed of light. Every piece of the standard model, every prediction of quantum electrodynamics, every test of general relativity, every confirmed property of every particle ever detected. All of it rests on the constancy of c. Removing that constancy doesn't just make interstellar travel easier. It demolishes the framework that explains everything we've ever measured. And we've measured quite a lot. The universe has given us no indication that it is willing to accommodate a theory that breaks Lorentz invariance at any energy scale we've probed. Tests of Lorentz invariance have been carried out with precision at the level of 1 part in 10 to the 20th, or better, using gamma rays from gamma-ray bursts, using neutrinos from supernovae, using data from atomic clock comparisons, using cosmic ray physics. No violation has been found. None. The light barrier is not just a theoretical result. It is confirmed by every measurement ever made. Something that often gets lost in popular discussions of this topic is the question of what theoretical physicists actually do with these ideas. The public version is, someone proposes faster-than-light travel, skeptics say it's impossible, the debate ends. The actual version is more interesting. Physicists don't just dismiss exotic ideas, they analyze them. They work out the consequences. They identify which assumptions are required and test those assumptions. They ask which versions of the idea might be salvageable and which are definitively ruled out. The Alcubierre drive went through this process. The initial paper was analyzed by dozens of researchers. The exotic matter requirement was quantified. Subsequent papers reduced it. The horizon problem was identified and studied. The Hawking radiation concern was raised and evaluated. The particle accumulation problem was calculated. The subluminal version was shown to be free of several of these problems. A general framework for evaluating all warp drive designs was developed. Numerical tools were built. This is what theoretical physics looks like from the inside. Not a binary judgment of possible or impossible. A systematic exploration of a space of ideas, with the impossible regions being mapped as carefully as the possible ones. The impossible regions are important. They tell you where the boundaries of what nature permits are. And the boundary of what nature permits is where physics is most revealing. The Alcubierre drive tells us something profound about the structure of general relativity. It tells us that the equations permit geometries that could in principle carry things faster than light, but that building those geometries requires physical resources that the universe appears to be unwilling to supply. That unwillingness is itself a fact about nature, a deep fact, one worth knowing precisely. There is a thought that deserves its place at the end of all of this: physics. Most of the universe is permanently inaccessible to us. Not just practically, permanently. The universe is roughly 93 billion light-years across in the observable sense, meaning 93 billion light-years of space from which light has had time to reach us since the Big Bang. But the universe itself may be much larger, possibly infinite. And it is expanding. The most distant regions we can currently observe are receding from us faster than light. Light emitted from those regions today will never reach us. It will be swept away by the expansion faster than it can travel toward us. The observable universe, already vast beyond comprehension, is a shrinking fraction of the total. As time passes, more and more of the universe passes beyond our cosmological horizon. It doesn't cease to exist. It simply becomes forever inaccessible. No signal we could ever send would reach it. No signal it could send would ever reach us. We are not just limited by the current state of our technology. We are limited by the structure of the universe itself, by the combination of a finite speed of light and an expanding spacetime. The universe is larger than the part of it we can ever know about, and it is growing more isolated from itself with every passing moment. Every galaxy beyond a certain distance will eventually cross our horizon. The stars in those galaxies will wink out one by one from our perspective, not because they've gone out, but because the space between us and them has grown so large that their light can no longer reach us. In the far future, long after the present stars have ended, the only galaxies visible in the sky of any civilization still around to look will be the members of their own local group. Everything else will have receded beyond the horizon. The universe will appear, from any local vantage point, to consist of a single gravitationally bound island of matter. The rest, the vast majority, invisible, gone not through destruction, but through expansion. The speed of light and the expanding geometry of spacetime together draw a permanent boundary around what any observer can ever know. And everything beyond that boundary is not just unknown. It is unknowable. Not because we haven't looked hard enough or built big enough telescopes, but because the universe has a structure that enforces this isolation. The light barrier is not just a constraint on travel. It is the architecture of cosmic isolation. Every star you see in the night sky is a prison of this isolation made visible, each one separated from its neighbors by distances so vast that even light takes years to cross them. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. 4 years and 3 months for light to make the crossing. For a physical object, under our best propulsion, the journey would take tens of thousands of years. The next nearest star is Alpha Centauri A and B, a binary pair at roughly the same distance as Proxima. Then Barnard's star at nearly 6 light-years. Then Wolf 359 at about 7.8 light-years. Then Lalande 21185 at about 8.3 light-years. The 10 nearest star systems to the Sun span a volume roughly 10 light-years in radius. Beyond that, the Milky Way extends for about 100,000 light-years. Beyond the Milky Way, the local group of galaxies extends for a few million light-years. Beyond the local group, the observable universe extends for 46 billion light-years in every direction. And beyond the observable universe, the universe continues, possibly without limit. All of it separated by distances that the speed of light makes effectively impassable on human timescales. And possibly, actually, impassable on any timescale if the geometric loopholes are indeed closed. This is the universe we live in. Not the universe of science fiction, where these distances are routinely crossed in hours or days. The actual universe, where the distances are real and the speed of light is real, and the two together draw a hard line around what any civilization, anywhere, can ever reach. And yet, the research continues. The subluminal warp drive is being developed because it is physically achievable in principle and would transform travel within the solar system and to nearby stars on timescales of years rather than millennia. The energy condition theorems are being examined for assumptions that might fail in quantum gravity. The quantum energy inequalities are being refined. String theory and loop quantum gravity are being developed toward predictions that might eventually be testable. Experiments testing Lorentz invariance at higher and higher energies continue. Not because physicists are naive about the odds, but because the universe has surprised us before. Quantum mechanics was not predicted from classical physics. It was forced on physics by experimental results that classical physics couldn't explain. General relativity was not predicted from Newtonian gravity. It was forced by a conceptual inconsistency in the combination of Newtonian gravity with special relativity, and then confirmed by observation. The history of physics is a history of the universe being stranger than expected, not in ways that break the light barrier, but in ways that reveal structures we didn't know existed. Quantum mechanics revealed that particles can be in superpositions of states. That measuring one entangled particle instantly affects another. That the act of measurement is not passive, but actively changes the system being measured. None of this was expected. All of it was forced by data. Whether the universe has more surprises of this magnitude waiting to be found, surprises that don't break causality, but that reveal structures near the light barrier we haven't yet seen, is genuinely unknown. Physics doesn't know, and physics is honest about not knowing. That honesty is one of the best things about it. Pull back from all the physics for a moment and consider what it means. Every part of the observable universe is speaking to you in delayed messages. Light from the moon takes about 1.3 seconds to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star beyond the sun takes over 4 years. Light from the center of the Milky Way takes about 26,000 years. Light from the Andromeda Galaxy takes about 2.5 million years. When you look at Andromeda with a pair of binoculars, the light entering your eye left that galaxy 2.5 million years ago. The universe you see when you look up is not a picture of now. It is a composite of snapshots taken at vastly different moments in the past. Some of those stars may no longer exist. Some of those galaxies may have merged with neighbors. The universe, as it currently is, the actual present tense state of the cosmos, is inaccessible to us. We can only know what the light tells us, and the light always tells us the past. What lies beyond the speed of light isn't just faster travel. It is real-time knowledge of the universe. The ability to exist in the same present moment as the things you can see. To ask a question of the stars and receive an answer from the stars as they are now, not as they were 100 or 1,000 or 1,000,000 years ago. That capacity, as far as we know, does not exist. Not for us. Not for any civilization, anywhere. If other intelligent species are out there, they face the same light barrier, the same delay, the same experience of looking out at a universe that reveals only its past. Everyone is isolated from the present tense cosmos, looking out through a window that shows the past with extraordinary beauty and zero capacity for current news. This is not melancholy. It is the nature of the universe as we have come to understand it. And understanding it precisely is the only honest response to it. Before leaving special relativity and its consequences, there is an aspect of the light barrier that deserves its own discussion. Time dilation, at near light speeds, does something that sounds like science fiction, but is perfectly real physics. It allows you to travel, from your own perspective, across vast distances in a subjectively short time, not faster than light, but with dramatically compressed subjective experience. Consider a spacecraft accelerating at 1 g, the same rate as Earth's gravity at the surface. Passengers would feel normal weight. Their bodies would function normally. Everything would feel comfortable. Now, accelerate at 1 g for a year. You reach roughly 72% of the speed of light. Continue accelerating. After 2 years of proper time, you're just over 90%. After about 7 years, you're past 99%. The time dilation at that point is enormous. Enormous from the outside. From your perspective, you've just been sitting in a 1 g field for 7 years. From the perspective of the outside universe, vast amounts of time have passed. Continue the acceleration for long enough, and you could, in principle, cross the galaxy in a human lifetime. Not because you traveled faster than light. Because at near light speed, the time aboard your spacecraft and the time outside become radically different. You age slowly while the universe ages fast. This is not a violation of the light barrier. It is the light barrier's most counterintuitive consequence. The very mechanism that prevents you from reaching light speed, the diverging energy requirement that makes each increment of speed cost more and more, is connected to the time dilation that makes large distances subjectively traversable. The universe built a consolation prize into the same physics that enforces the limit. You can't get there faster than light. But if you're willing to spend enough energy, you can experience the journey in as little time as you want from your own perspective. The energy cost is astronomical. For a macroscopic spacecraft and its occupants, the energy required to accelerate to the near-light speeds needed for meaningful time. Dilation is beyond anything human civilization currently produces by orders of magnitude. But the physics permits it. The barrier forbids you from arriving before the light. It doesn't forbid you from arriving while still alive. The difference between those two things, between arriving before the light and arriving while alive, is the difference between violating causality and exploiting it cleverly. Near-light speed travel doesn't violate causality. Every observer agrees on the sequence of events. You depart. You travel. You arrive. In the right order. From every perspective. The travel takes a long time from the outside perspective and a short time from yours. But it's not instantaneous. Light from your departure can still reach the destination before you do. The causal order is preserved. The connection between cause and effect is unbroken. This is why near-light speed travel, for all its strangeness, is considered unproblematic from a causality standpoint. It uses the asymmetry between reference frames without breaking the fundamental ordering that physics requires. Faster-than-light travel, by contrast, breaks that ordering. There are always reference frames in which faster-than-light travelers arrive before they leave. Reference frames that are just as valid as any other, with no absolute frame to adjudicate between them. The arrival before departure is real from those frames, and the universe has no mechanism to prevent logical contradictions from arising. The distinction between these two cases, near light versus beyond light, maps exactly onto the distinction between strange but consistent and strange and contradictory. One is physics. The other is a broken universe. There is an experimental aspect of this topic that doesn't always get the emphasis it deserves. The search for violations of Lorentz invariance. Lorentz invariance is the symmetry of special relativity, the property of physics that makes the speed of light the same for all observers. If Lorentz invariance were violated at some energy scale, it would be a signal of new physics. New physics that might modify the light barrier in ways we haven't anticipated. Physicists have searched for such violations with extraordinary precision. The most stringent tests use astrophysical sources of high-energy photons. Gamma-ray bursts are among the most energetic events in the universe. They produce photons across a wide range of energies. If Lorentz invariance were slightly violated, different energy photons would travel at slightly different speeds. Over the billions of light-years separating us from distant gamma-ray bursts, even a tiny difference in speed would accumulate into a measurable arrival time difference. The Fermi Gamma-Ray Space Telescope has measured arrival times of gamma-ray burst photons across a range of energies. The results set limits on Lorentz invariance violation at the level of 1 part in 10 to the 20th. This means that if Lorentz invariance is violated, the violation must be smaller than 1 part in 10 to the 20th. That is an extraordinarily tight constraint. To put it in context, the precision of modern clocks is about 1 part in 10 to the 18th. The tests of Lorentz invariance are 2 orders of magnitude more precise than our best timekeepers, and they find nothing. No violation, no hint. Similar searches using cosmic ray data, atmospheric neutrinos, comparisons of atomic clocks, and analysis of gravitational wave signals from merging black holes and neutron stars have all found the same result. Lorentz invariance holds. At every energy scale we have tested, to precisions that would have been unimaginable a generation ago. The light barrier is not weakening at high energies. It is not being modified by new physics at the scales we've probed. If new physics modifies Lorentz invariance, it does so at energies or scales beyond current experimental reach. The experimental picture is unambiguous. The limit stands. What would it take to change this picture? What kind of new physics could, consistently with everything else we know, open a door beyond the light barrier? It would have to satisfy extraordinary constraints. It would have to preserve the confirmed predictions of the standard model of particle physics. Every prediction of quantum electrodynamics. Every calculation that matches data from particle accelerators. Every confirmed property of every particle ever detected. It would have to preserve the confirmed predictions of general relativity. The bending of light by gravity. The slowing of clocks in gravitational fields. The existence and properties of gravitational waves. The dynamics of binary pulsars. The expansion of the universe. It would have to resolve the causality paradox of the tachyonic antitelephone. It would have to explain how faster-than-light signaling doesn't enable logical contradictions. It would have to be consistent with the no-communication theorem in quantum mechanics, while somehow circumventing it for some class of systems. And it would have to avoid violating the experimental limits on Lorentz invariance, which are now at the level of 1 part in 10 to the 20th. This is not an impossible list. Physics has been surprised before. But it is a very demanding list. Any proposal that satisfies all of these constraints simultaneously would be extraordinary. And any proposal that violates any of them without explaining why the violated constraint turns out to be wrong would not be taken seriously. This is what separates serious theoretical physics from speculation. Not that speculation isn't allowed. But that speculation has to eventually connect to the existing framework in a way that preserves what's confirmed while genuinely adding something new. No proposal for faster-than-light physics has yet met that bar. Not from lack of trying. From the extreme difficulty of the constraints. Before we arrive at the final picture, there is one more dimension of this topic that deserves its full treatment. The question of what science thinks beyond light speed is also a question about the fate of interstellar civilization. If the light barrier holds absolutely, if there is no geometric loophole that physics permits, then the structure of the cosmos has a specific implication. Civilizations are islands. Not just isolated by the practical difficulty of interstellar travel, isolated structurally. Isolated by the physics of the universe they live in. Any civilization, anywhere, faces the same light barrier. An advanced alien civilization on a planet orbiting a star 100 light-years from Earth cannot reach us in less than 100 years, regardless of their technology. The physics applies to them as it applies to us, if they exist. If they have built radio transmitters or spacecraft or any technology at all, they still live in the same universe, governed by the same equations. This may be part of the answer to one of the oldest questions in all of science. The Fermi paradox. Enrico Fermi, the physicist who built the first nuclear reactor, it was having lunch with colleagues in 1950 when someone brought up the recent news coverage of reports of unidentified flying objects. After a brief calculation on the back of an envelope, Fermi asked a simple question. If the universe is old and large, and if other intelligent civilizations exist or have existed, where is everybody? Why haven't we heard from them? Why haven't they visited? Many answers to this question have been proposed. Maybe intelligent life is genuinely rare. Maybe civilizations tend to destroy themselves before becoming interstellar. Maybe they're here and we're missing the signals. Maybe they're communicating in ways we haven't thought to look for. One possibility that fits naturally with the physics of the light barrier is this. Maybe interstellar travel is simply too hard. Not just for us, at our current level of development. For any civilization. Ever. Maybe the distances, combined with the speed of light, constitute a barrier that no amount of technology can fully overcome. A civilization 1,000,000 years ahead of us in technology still lives in the same universe. They still face the same light barrier. The energy required to accelerate a spacecraft carrying biological beings to a significant fraction of light speed, sustaining that acceleration over the years required for an interstellar crossing and then decelerating at the destination, is enormous by any reasonable estimate. Even if they solve the energy problem, they still face the time problem. Even at 99% of light speed, a journey to a star 1,000 light-years away takes over 1,000 years by the outside calendar. The crew ages more slowly, but they're still committed to a multi-year journey from their own perspective. And the universe is big. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. If you wanted to explore even 1% of them, the travel time, even at near light speed, would span timescales comparable to the age of the universe. The distances aren't just large. They are in a different category from anything human civilization has ever dealt with. And the light barrier ensures they stay that way, unless the geometric loopholes turn out to be real and accessible, which may be exactly why physicists keep working on them. Not out of naive optimism, out of an honest desire to know whether the universe permits us to leave home. And if it doesn't, whether that answers Fermi's question permanently. There is another consequence of the light barrier that is rarely discussed, but is genuinely strange. If faster-than-light travel is impossible, and if other civilizations exist at interstellar distances, then we are each enclosed in what might be called a light cone prison. Not a prison in the sense of suffering. A prison in the topological sense. A region of space-time from which we can reach only the events that lie within our future light cone. The future light cone is the set of all space-time events that can, in principle, be reached from our current location at or below the speed of light. Everything inside the cone is reachable. Everything outside it is not. And as time passes, our light cone expands. Each moment, the boundary of what we can, in principle, reach grows larger. But the rate of expansion is c, and the universe is also expanding. The net result is that some regions of space that are within our reachable volume today will, over the coming billions of years, be swept beyond our light cone by the expansion. They will become permanently unreachable. Not because of anything we did, not because of any failure of technology, because the universe expanded them beyond the boundary while we were alive. The light cone prison has walls that are closing in, not from all sides, but from the outside. As the expansion of the universe progressively contracts, the volume of space that is forever accessible to any fixed observer. This is one of the strangest consequences of living in an accelerating, expanding universe with a light barrier. We are each embedded in a shrinking sphere of cosmic accessibility, and there is nothing to be done about it. It is simply the nature of the universe we were born into. Despite all of this, or perhaps because of all of it, the question of what lies beyond the speed of light generates some of the most creative and rigorous physics being done today. The people working on warp drive metrics are not dreamers with no connection to reality. They are mathematical physicists with serious credentials, publishing in peer-reviewed journals, being cited by other physicists, building on each other's work in the normal way of science. The question is genuine. The tools are real. The results, while not yet pointing toward a working drive, are advancing the field of gravitational physics in ways that have independent value. The study of energy conditions in general relativity has been sharpened dramatically by the need to understand which configurations of matter and energy can support warp drives or wormholes. The taxonomy of space-time geometries has been extended by the systematic frameworks developed for warp drive analysis. The understanding of Hawking radiation in non-static geometries has been advanced by the study of moving warp bubbles. These are not small contributions. They are part of the infrastructure of theoretical physics. The fact that they haven't produced a faster-than-light vehicle is not a failure. It is the normal result of pushing against a hard boundary. The boundary pushes back, and the pushback is informative. Every time a proposed mechanism turns out to be blocked by an energy condition, or requires exotic matter, or produces an event horizon that breaks communication, or sweeps up particles into a lethal beam, that result is telling you something about the structure of the universe, about the thickness of the walls surrounding the light barrier, about why the universe is organized the way it is. Physics at the limit is the most revealing physics there is. Consider also what the light barrier means for contact between civilizations. If two civilizations separated by 1,000 light years want to exchange a single message, the reply cannot arrive for at least 2,000 years. A conversation with a round-trip delay measured in millennia is not a conversation in any normal sense. It is more like finding a message in a bottle on a beach, and knowing that whatever you write back will reach the sender, if they're still alive, long after everything has changed for both of you. The light barrier doesn't just make the universe hard to travel through. It makes it hard to know, hard to communicate with, hard to form any kind of relationship with, in the extended sense of relationship that requires actual exchange. Every civilization that has ever existed, if others exist, has faced this same wall. The message, from Earth's television and radio broadcasts, which began propagating outward in the 1920s and 1930s, has now reached about 100 light years into space. A sphere 100 light years in radius. A volume that contains perhaps a few thousand star systems. If any civilization around those stars is listening and responds immediately, the first reply could arrive around the 22nd century. And that reply would be about us as we were 100 years ago, before the sender could know anything about us now. Communication at light speed across interstellar distances is communication across time, always delayed, always historical, always a connection between different epochs rather than a real-time exchange. The universe has a structure that makes intimacy between distant things impossible, not through hostility, but through geometry. It is simply too large, and light is simply too slow, for anything to be truly simultaneous at cosmic scales. The picture science has assembled is precise, honest, and neither hopeful nor pessimistic in the way those words usually mean. The barrier is real. Crossing it conventionally is impossible. Getting around it through space-time geometry is mathematically permitted and physically blocked by obstacles that are themselves rooted in fundamental physics. The prohibition on faster-than-light information transfer is the deepest constraint of all, because it connects to the logical consistency of the universe rather than just its energetics. And the question of what quantum gravity says about everything in this picture is genuinely, honestly open. That openness is precision. We know where the edges of our knowledge are. Those edges live at the Planck scale, where the smooth space-time of general relativity gives way to something discrete and quantum that we don't yet fully understand. Somewhere in those equations, either a definitive closure of every loophole or the first hint of a door is waiting. Either answer changes the picture. Either answer is profound. A universe that closes every loophole definitively is a universe where every part is forever isolated from every other part beyond light years' distance. A universe where a door exists somewhere in the geometry is a universe that has more structure than we currently know about. And the search for which one we live in is one of the most honest things science does. Standing at the edge of what is known, asking without flinching what lies beyond it, and accepting that the answer may be nothing we can reach. That is what science thinks happens beyond light speed. Not a single sentence. Not a simple answer. A carefully built structure of reasoning that takes you as deep as current knowledge reaches, and then points, with precision and honesty, at the darkness past the edge. Good night.